Okay, thank you, everybody. Thank you for the very kind introduction. This topic is, I think, relevant now because so much of what I see from design guidelines online, it seems like all the old, sometimes bad recommendations get recommended anew as being applicable in modern PCBs with DC components and with digital components, or with low to mid frequency components and digital components. So this continues to be an evergreen topic. Let's look at what happens in a typical mixed signal PCB. Typically in a mixed signal PCB, we have some challenges in the layout. In the layout, we may have, for example, an analog front end. Part of that analog front end might be high frequency, so there might be an antenna. You might have an RF input in some systems, for example, coming through like an SMA connector, and then that needs to be routed to an RF front end. You'll then have some high-speed digital component somewhere maybe in the middle of the board. That's usually your microcontroller, your microprocessor, maybe an FPGA. There's usually some other components, low-speed digital. Then you'll have a power section somewhere. And so these are all the different components that typically appear in a modern mixed signal board. So most of the EMI, SI, PI problems that appear in mixed signal systems, they tend to start in the PCB stackup, and then related to the stackup is, of course, grounding. So within the stackup, you assign layers for signal and for ground. Sometimes you assign them for power if you're dealing with a power system. And some of those simpler problems, many of the simpler problems, can be eliminated with the right stackup, and through the stackup, the right selection of grounding and places to route signal. So what I like to do in this presentation is start with some beginner's mistakes. And it's these beginner's mistakes that lead to problems in mixed signal systems. So the layout example I'm showing here is a clone of an STM32 dev board. It was sent in for one of our 1-minute design reviews, and I'm not going to pick on anybody through this, but I will say the person who sent this in, she later redesigned it and actually did a very good job on the redesign and eliminated what would be some common SI problems just through a simple redesign. But here are some of the common rules that we can pick out from some of this type of board. And you've probably seen this on example for an Arduino. Some of the common rules are you have to flood everything with grounded copper. There are reasons to do it, but you don't have to do it on every board. There are good reasons to do it on some 2-layer boards, but in some cases you just want to go to a 4-layer board. The one that keeps coming up over and over again is separating analog and digital ground planes. And what I mean by separate is not separate the components into 2 different regions of the board as I show here, but rather to separate analog and digital ground planes into totally different pieces of copper. And then there's kind of a contradictory rule on top of that, which is that you only need ground planes on whatever an advanced design is. It's not clear what advanced design is supposed to mean, but the common beginner's mistake is that, well, I don't need a ground plane. But if I do, I should separate them into analog planes and digital planes. The next one is to put stitching vias everywhere. I think there's a misunderstanding of why stitching vias are used, but nevertheless, the beginner's mistake is to put them everywhere. Then we have the interesting one, which again comes up again and again and again, which is the magic bullet to filter noise is to use ferrites. Ferrites are useful, but they're not useful for everything. And then if you do have your separate analog and digital ground planes, you have to bring them back together to set them to the same DC potential using a ferrite. So you don't want high frequency noise to pass between the 2 planes. So theoretically, grounded in a basis for how the ferrite is supposed to work, but of course, for those of you who have seen my talks on EMI, this is of course an EMI problem. The next one is that via transitions are generally bad. I don't know where this came from. I think this is something that originated from RF design. And then, of course, everyone said, well, you know, my little Arduino board shouldn't have via transitions either, which is also just incorrect. Guard traces should be used between signals. Guard traces only work in, I think, 1 out of 6 instances, and in other instances, they do nothing to crosstalk, or they will make crosstalk worse. The big common one here, second to last point, is the clock frequency is what determines your SI problems. That's also incorrect. Your clock frequency is not what's responsible for signal integrity problems. It's actually the edge rate. And then here, the last one, the corollary to the ground planes are only in advanced designs is that 4 layers is just too expensive for a hobbyist or student. If you've ever done any pricing overseas, for example, in JLC, you will know that, yes, 4 layers is more expensive, but the payoff you get is worth the additional investment in 2 additional layers. So now, in these stackups, sometimes you will see that when we place pour, it then totally covers these traces. Sometimes you get these little antennas, as you can see right here in this region between these 2 traces. But generally, we try to make sure that this pour totally encloses the traces. And what it does is it provides a capacitively coupled return path. So this is a really common practice that's used on 2-layer boards, whether it's mixed signal or digital or whatever. This is one common practice. So if you place the pour, it can provide this capacitively coupled return path. And then in order to balance the copper, if you place the pour on one side, you have to place it on the other side in order to balance the copper and then suppress leak warpage. So that's typically the guideline that you'll see. So in some cases, it is totally appropriate to do this. In other cases, I would say it's not appropriate to do this because at some point, this 2-layer board gets so dense that you don't get any additional benefit from the copper pour. So what really matters here for using the copper pour as your ground for your system is the component density. And as we're going to see soon, grounding is very important for ensuring that your mixed signal board works correctly because it determines where the return current is located. And if you can isolate your circuits into different parts of your board, then you can control where those return currents are located. And that's how you prevent interference between different circuits. So this slide shows some different stack-up options for the cases where you do get to a very dense 2-layer board and need to add 2 more layers in order to provide ground. There are some variations of this that I've seen people discuss with me recently and have asked questions about for videos, and so I decided to show them here. What we see here are the 3 typical options for 4-layer stackups. The best option here in the center is option 1. This is a stackup that is perfectly appropriate for mixed signal boards, also for high-speed boards. This is the type of stackup that you would see used in, for example, a motherboard that doesn't have very high density. This is a signal power ground signal power type of stackup. So it's a very useful option. Option 2 basically just inverts option 1. And this one gives you some shielding on the outside of the stackup. However, you now have the potential for some level of coupling between these signals on the inside of the stackup. So as long as you're not making large parallel routes between these 2 layers and you're doing everything with orthogonal routing, option 2 is just fine. Option 3 is probably the most commonly selected stackup when someone first starts doing 4-layer boards. However, I think it's the one that's most misused. Signal and ground here up on the top half of the stackup. This allows your circuitry to ensure that its return current is very closely aligned in this ground plane. And this would apply in high-speed boards, purely analog boards, or in mixed signal boards like we're discussing here. The other plane layer here with power. Now, power can be used on this 3rd layer, and then you can have signal above that power. The issue here is that those signals are going to have a hard time coupling their return path back to ground due to the capacitance between the power plane and the ground plane. So this is what gives you the potential for strong radiated EMI. And so there are some tricks that you can use if you have to put high speed signals on the bottom layer, but really I think it's better to just go with option 1 if that's the case. For option 3, you could use DC signals. You could use very slow edge rate signals and put those on the back layer, configuration signals, things like that. That's perfectly fine to put those on the back layer. But this type of system is really something that I think is more for specialized power systems. This is the type of stackup that I've used in power systems that have a digital interface. So for example, this would be like a power system that has a microcontroller located on the board, and it executes some power management functions and communication with an external system and things like that. So option 3 can be used for mixed signal or for digital systems, as long as you actually need the power plane to provide high current. So between these two options, where we have signal power ground, ground signal power, which one of these is going to be most useful for a mixed signal board? Well, I maintain that in all cases, you would have the option on the left being the best option for a mixed signal board. Here, it requires you to route power as large rails or as traces. And that's perfectly appropriate, even in systems where you have a big processor. The power demands for some components can be high, but it's not so high that you necessarily need to have a power plane. And in fact, in this type of system with option 3, one of the reasons that you might use a power plane is because it gives you some convenience for getting power over to the components up here on the top layer, without having to route any dedicated power traces. So if you can keep your analog stuff in one region on the top side, and then your digital stuff on one region on the top side, you can then actually make routing a bit easier for yourself in terms of power by having this internal layer dedicated for power. And in addition, with this power layer, it doesn't have to be one plane at one voltage. You could actually split this up into multiple rails, and those multiple rails could have different voltages. So one thing that's actually quite common in mixed signal boards is you have different voltage levels, and some of those voltage levels are non-standard. For example, you could have 3.3 volts for logic. You could have also have 5 volts for logic. Maybe you have a higher voltage for your input power. But then you might also see, for example, a lower level voltage value. For example, maybe 1.25 as the reference for an ADC. So those are all things to consider when using a power layer. That power layer gives you a lot of flexibility to get power to components without having to route the power in the same layer as your signal. So as I mentioned here, there is the potential for crosstalk between these layers when you are using the stackup here on the right. Now, the stackup here on the right is very nice because it shields you from external radiation just as effectively as the stackup on the left. However, there's no shielding between the layers. Really, the shielding between the layers is only accomplished by coupling directly to the ground plane on the next layer. Now, could you do some layout here where, for example, on the left side, you only have your analog stuff, and then on the right side, you only have your digital stuff? Yeah, that's possible. You can do that. Is it practical or is it easy? Well, I think if you're going with this type of stackup, you're making things a little more difficult for yourself. And what you might consider doing is instead having a mixture of option 2 and option 3, where the top half is this ground and signal, and then the bottom half is power and ground. So this is another stackup that we recently discussed in a video. By doing that, you could then have that convenience of having a complete layer for power, just in terms of getting power to where it needs to go. You could break it up into multiple rails if you want to. And as long as you are not operating with extremely high frequencies or very fast signals, you can put those signals on this internal layer on layer 2, and those can route around to your components up on the surface. So I mentioned earlier that we need to have a return path confined somewhere for our signals. And so this is really what determines where or whether two signals can interact with each other or appreciably interfere with each other. here in the signal ground power signal type of configuration, if we do have this situation where we have a component that is driving either a digital signal or a analog signal to a receiver on the top layer, and that component is capable of conducting coupling a return path into the plane layer on the next layer. Here, if we couple that into the power plane, that signal is going to be trying to get back to the ground plane here on layer 3. Well, here there's really no direct connection between power and ground, at least through a conductor. Of course, that would short circuit power and ground, so that would be a bad thing, right? We don't want to short circuit power and ground. And so what this signal tries to do is it tries to couple its return current over to the ground plane, and there's really no clear return path. So there's the possibility for emitted radiation, and then there's also the inability to accurately predict where the return path is even located. And actually what ends up happening is there is return current in the power plane, but that return current ends up getting back to the ground plane, usually through the nearest capacitor. So there's probably going to be a capacitor somewhere between power and ground that helps provide stable power between for the driver and then also for the receiver. And then the return current can usually flow through that. And so the result is that you actually aren't sure where the return current even exists, and you could get a very big inductive loop for certain signals. So this is one of the reasons why we don't want to put the fast digital up here on this top layer. Now, when we have a faster digital signal, we get greater confinement of that return current in this region right below the trace. So think about that now in terms of what happens with mixed signal at very low frequencies. What happens with very low frequencies? Well, with lower frequencies, there's less of an ability to confine that return current here in this region below the trace. So with lower frequencies, we may need to use some tricks in this stack up, for example, applying copper pour. Now here's an instance where the copper pour actually becomes useful, because that copper pour up on this top layer can provide a better return current coupling into ground, and then you would use your stitching vias to get back to the ground in layer 3. So this is just one of the instances where we can get some usefulness out of copper pour. It's not one of those things where we absolutely have to use it in every design, but it's helpful here in this situation where we do have to have signals on this back layer, but we don't have a clear return current path. And we'll show some examples of that here later in the presentation. Okay, grounding. Now, grounding is one of the most important issues in mixed signal design, and grounding comes up again and again and again as a challenge in terms of EMI creation. It also comes up again and again in terms of a challenge of SI. So we really have multiple problems here that can be solved just by having a good ground throughout your PCB. Now, the other thing I would bring up here with grounding is that once you get to more advanced designs, and I'm going to qualify what advanced means, once you get to more advanced designs where you do have very fast digital signals, the right grounding strategy in your stack up also influences power integrity. So the power integrity aspect, I think, gets rightfully overlooked in mixed signal PCBs. Mixed signal PCBs tend to be operating at lower edge rates. They tend to be operating at lower frequencies. You don't necessarily need to have large ground planes on multiple layers directly next to power planes in order to provide stable power. So I mentioned a few different times about grounding with the return current. So here I have a graphic that I made many years ago, which is intended to illustrate some reasons why we don't want to have split grounds or totally disconnected grounds, as is sometimes recommended when looking at mixed signal PCB design guidelines. So here in the top layer, what I'm showing is just a very simple board. And what I show here in this dashed line is the ground plane on layer 2. Now, as I mentioned before, if we send in a signal, let's say into this integrated circuit through this trace, and this trace is routed over this slot, what happens is eventually that return current has to return through this ground plane. Now, some of this current is, of course, coupled into the ground plane through the capacitance between the trace and the ground plane. But some of that current also just passes through the ground pin and then follows this circuit loop back to the input. So this is a really simple way to think about where the return current exists. Now, of course, that return current has to exist in a conductor, and we can see where it has to exist in the conductor. It has to then follow around this path where we have this split in the ground plane. And so this is the big reason that we don't want to then try and split our grounds in a mixed signal PCB. It's because in this region where the return current has to route around this slot in the PCB, we can then get radiated emissions from this region. Now, we would like to ensure that in this side view, we have the smallest possible loop for this signal. And that smallest possible loop occurs when we can bring this return current as close as possible to this trace. So no matter what, in this side view, the side view is always going to have this loop, but we want to keep the loop even tighter by bringing this return current close to this trace. And so the only way to do that is really to then close this slot between these two regions of this PCB. Now, what would be the other reason, or would the other possibility? Well, of course, the other possibility would be to put the source of this signal over here by this integrated circuit. But if we do that, and then we leave this slot here, what would we have to do? Well, we'd have to avoid doing any routing in the region of this slot. So I'll show some more examples here just conceptually as we go forward. Now, what would happen if, for example, we have a total disconnect between the region on the right where we have the integrated circuit and then the region on the left where we have our signal originating? What would happen? Well, if we had these two regions of copper totally disconnected, we would have two possible things that would happen. First, of course, if we try to route a signal over that complete disconnect, such as you see here in the lower third of this slide, we then get very strong radiated emissions from this region between these two planes. And that return current kind of exists everywhere and nowhere simultaneously. And it might try and then couple back between these two sides back to its input capacitively, maybe through some components. It's very difficult to predict where exactly it will exist. But in any case, you would then have a big source of radiated emissions here in this region where you have this split. Now, there's something else that happens when you have two different ground offsets, or two different grounds in two different regions of a PCB, such as I show in the bottom slide here. You can have what's called a ground offset. So suppose that these are isolated grounds, meaning that they're galvanically isolated from each other. They can develop a potential difference between them. So when they have a potential difference between them, what that means is that if I source a signal on the left side with respect to ground number 1, and I measure its voltage, I would get V1. Well, if ground 1 and ground 2 have a voltage offset between them, meaning if I take the voltage ground 1 with respect to some other ground, let's say Earth, and then subtract the voltage on ground 2 with respect to some other ground, let's say Earth, I might get a value of 0. Well, then the result is that if I measure V2, I don't get the same voltage as V1. So this is called a ground offset. And this occurs when you have two floating grounds. And that's exactly what you get when you take a PCB like this, and then you split into a digital region and an analog region, and you have them totally disconnected. So you don't have this small section here to then couple the return currents. So when you have that isolated floating grounds, and then you try to route a signal over them, you get the same situation as we saw before, which was strong radiated emissions. Now, let's just suppose for a moment that here you see I'm routing a single trace. I always like to, I've been asking this recently because it's always interesting to see what people say. What if instead of having just a single trace here, what if this was a differential interface? So let's say, for example, this was a differential ADC, and we wanted to measure, let's say, the differential voltage coming along this interconnect from, let's say, a sensor that has a differential output. Now, where does the return current exist? Well, if this is a true differential interface, then the return current exists partially in the copper plane, but it also exists in the other trace. So this is one of the big reasons that differential signaling was even invented. One of the reasons it was invented was so that you could route between different pieces of equipment that have what are essentially floating grounds between them, and it eliminates this voltage offset. So rather than taking the voltage difference between a trace and two different planes, what a differential interface does is you would have two traces here, and you're just measuring the voltage between the traces. So differential interfaces are actually quite important in mixed signal PCBs, where you have a sensor, and the sensor has a differential output. And it is that differential output that allows you to route those two wires around, let's say plug them into a PCB, and then be able to get that signal into a differential interface like a DAC, like a ADC, or for example, a differential amplifier, and then read what the signal is coming off of that sensor. So the same principle applies in high-speed differential pairs, but we use differential pairs with high-speed signals for a different reason. And so I think that's something we could get into maybe in a future presentation where we talk more about high speed. So what is the frequency where we start to care a lot about the return path, particularly in high-speed PCBs versus a mixed signal PCB? Well, here what I'm showing in the top half of this image is a simulation result that illustrates what happens to the return current around a slot in a ground plane. Now, most PCBs are not going to be designed with this kind of slot like this. Probably the number one time you will see this is if you need to create a slot for a monopole antenna, but then you wouldn't want to route underneath it. Now, in this example, of course, this trace is being routed over this slot, and then you can see in green in the ground region where the return current exists. So it's this current loop around this region that then gives you that strong radiated emissions. Now, the extent to which the current is confined beneath this trace in the ground plane, that really depends on the frequency of the signal. Now, with digital, of course, we're dealing with fast edge rates, and so the bandwidth of that signal extends technically out to infinity. And so there may be some portion of the return current which is not tightly confined in this region below the trace, but most of that return current will be. And that arises because, of course, if you're familiar with Fourier series, digital signals are really just a construction of a bunch of sine waves, and those sine waves can span down to very low frequency. So it is possible that there is some return current in this digital signal that doesn't really tightly couple below this trace, but most of it will couple below this trace. And so that's one of the reasons why we want to have uniform ground everywhere over here, especially if we're dealing with digital signals. Now, what about our analog signals? Well, analog signals are very often harmonic signals, or they might be a harmonic signal but with comparatively small bandwidth around some carrier frequency. So here in the lower half, what I'm showing here is some simulation results, I believe from Bruce Archambault, that were published in the IEEE article. And these simulation results show the return path over a ground plane for a 1 kilohertz signal and a 1 megahertz signal. So either of these signals could be quite common in a mixed signal PCB. Now, what we see in the left-hand side is, of course, when we have the 1 kilohertz signal and we have our source and our load, and we're trying to put that signal around a trace as outlined here around the edge. We can see that most of the return current actually just passes directly between the source and the load in the ground plane. So here you have a really big circuit loop that defines the path for current. You see here it starts here at the source in the upper left corner, travels around the trace, and then travels to the load. The return current does not also travel that same path. And so you get this big inductive current loop. Now, why is that a problem? Well, that's a problem for two reasons. One is, of course, you do get some emissions from this. But the other reason is that it creates a big inductive loop that allows interaction with the magnetic field from some other circuit. So some other circuit can more easily induce noise in this type of configuration. So this is where we start to get some of those recommendations to start splitting ground. And the idea is that, well, if I split some ground here and maybe I apply a cutout in this region, the current is going to have no choice but to flow around the trace and tighten up that return path. And that is true. It will force the current to do that. The problem with that is now you have this big region in your PCB where you can't route anything, because then you would get the situation that's shown up here in the top half where you now have a region of strong radiated emissions. Now, conversely, look at what happens with the 1 megahertz signal. In that 1 megahertz signal, the return current is very tightly coupled below that trace. And so here it should be quite obvious that we wouldn't need to do anything with a slot here when we have that 1 megahertz signal. The return current very nicely just couples itself into this region below the trace, and it wouldn't necessarily matter whether or not this section of ground shown in dark blue is here or not. Now, it doesn't matter for this signal, but what about signals on other layers that might couple to this same ground plane? Well, of course, same thing. If I were to, let's say, cut out some ground here, it's not going to do anything to the return current for the 1 megahertz signal, but it will create this situation if I cut out some ground and then try and route below this 1 megahertz signal. You would then get back to this same situation where you now have a big antenna that is then possibly creating a situation that creates radiated emissions testing failure. So what happens here, or what I'm showing here, is one of the recommendations that we see with digital ICs and analog ICs where they have split planes. And so here I'm just showing the simple case where, again, we have a single trace routing between the analog and the digital interfaces. Basically, this digital IC could have an ADC built into it, and then this analog IC could be sourcing a current over to the digital IC, or vice versa. Just as an example, this could be a DAC with a digital interface. It then sources a waveform over to the analog IC, and then we need to have some path for the return current in both cases. And so here it's quite obvious where this lack of the return current exists. So here, because we've already segmented the digital stuff and the analog stuff, we don't really need to provide this split here in the ground plane because all we're doing is creating an inability to track the return current and then creating a source of EMI. So you would expect emissions in this region where ground is removed. So what's one of the proposed solutions here? One of the most commonly proposed solutions I see here is to then link these two plane regions back together with a capacitor. Now, you can do that, and you could put this capacitor right next to this trace. And so now the idea is that this capacitor is going to provide a return current path for this signal that's traveling between this digital IC and this analog IC, or vice versa. Now, of course, what's the problem with this? Well, this works for very high frequencies because at high frequencies, a capacitor has very low impedance. And so it's very easy for the current to then pass from one side of the capacitor to the other as a displacement current. So sure, this works fine for high frequencies. This fails for low frequencies because at low frequency, you basically just have this situation again where the capacitor looks a lot like an insulator, and so it doesn't emit a return current across it, and then you still have emissions at low frequencies. So what's the other problem with this? This is, of course, only showing one trace, but you might have, for example, a system that has, let's say, 10 or 20 or 30 traces. Do you really want to go through and place a capacitor across every single gap here for every single one of those traces in order to provide that return current? I would say no. That's extremely time consuming. Also, it doesn't help at all for the low frequency edge of the power spectrum for this signal. You'll still have low frequency emissions. And then consider this just from a practical standpoint in your CAD software. If you were to do that and place capacitors everywhere for each one of these signals, what if you had to rip up some of your routing and do rerouting? Well, now you have to go back and then also move this capacitor so that it's right next to the region where you did your rerouting. So that's also inconvenient. It could also create a problem with placement because now wherever I move that capacitor, I might have to move something else just to fit the capacitor in the right place. So this is one of the most commonly suggested solutions here to allow someone to split ground planes and then try to eliminate the EMI problem that they just created by splitting the ground planes. But then it creates all this extra work, and so I think there's really no point in doing this. Now, another thing here. What if we do everything correctly in the top half of the board, where we have our two ICs, we have our digital IC and our analog IC, and then we route here in this region where we have the uniform ground? Well, here we would then, of course, expect the return current reasonably to exist somewhere around this trace, unless we're at lower frequencies. However, with lower frequencies, there are some tricks we can use, such as using differential interfaces, and then that allows us to confine the return current where we want it. Now, one thing that sometimes comes up is sometimes we have a cutout. And these ground cutouts can be implied intentionally. You could have ground cutouts due to requiring clearances, for example, for certain mechanical components that have to press through the board. There are any number of reasons why you might apply a cutout. Now, one thing I've actually gotten into an argument about with some people who are much more experienced than myself is that they will say, well, you should never have a cutout ever. And I tend to agree with them. However, if you do have a cutout, simply having the presence of this cutout here does not create a radiated emissions failure for your mixed signal board, or frankly for any other board. As long as you don't route in this region, you're not going to automatically fail a radiated emissions test. And so the thought experiment that I always bring up about this in order to justify why it is okay to have a ground cutout, just don't route in the region of the cutout, is to think about this. What if you had kind of an odd U-shaped PCB? And so there was no dielectric here, but you filled in everything with ground, and then you just routed in the region where you have the ground plane. And if you did everything correctly, it passed radiated emissions testing. If you then just filled in this region where you had a U-shaped board with dielectric and left everything else the same, would you expect the board to suddenly fail radiated emissions testing or to have some sort of problem with mixed signal crosstalk? Well, I would say no, you wouldn't expect that at all. So that just justifies the point that it is okay to have a cutout, you just can't route anything in that cutout region. Now, what I'm showing here, where we have these analog regions and then these digital regions, and then they're brought together with some copper between them. This is sometimes called star grounding. Now, I think the spirit of star grounding is actually much different. It's not a large piece of copper, possibly with a cutout, but typically with star grounding, you will see these much more dispersed regions of copper to provide ground. And then you allow the signals to then kind of return only within those regions where you've applied star grounding. Now, this is a top view, kind of what we saw earlier, but where we've segmented the board into two sections, a digital ground section on the left and an analog ground section on the right. And then here we have basically some sort of input where we have, a plus terminal and a minus terminal. Now, here on the left side of our star ground topology, we have a digital IC, and the digital return current is going to exist somewhere in the copper on this left side. Here on the right side, we have an analog IC, and then also its return current is going to exist somewhere on the top side. Now, I say this is usually a bad idea because what happens if we have to route something between the digital IC and the analog IC, right? That's actually quite common in mixed signal boards, right? Let's say this is our microcontroller. Our microcontroller on the left needs to control some interface on the analog IC on the right? So this could, for example, be an ADC or a DAC, and those are, of course, digitally controlled. They may have an I2C or an SPI interface, and that's going to be controlled by your microcontroller. Well, in this idea where we have this kind of star point grounding, where we have one ground region for digital and another ground region for analog, where would we be required to route those signals? Well, if we were routing those signals directly from the digital IC to the analog IC, we would have to route them up along this region going north, and then east along the top part of the board, and then down here to the analog IC. So that's really inconvenient routing. Why would you want to route your digital IC signals from here around like this and then down to the analog portion? So that's very inconvenient. And then, of course, the natural solution is, well, just eliminate star grounding, allow your ground to be here, and then you can route directly from the digital IC to the analog IC. So star point grounding is usually a bad idea because people tend to implement it in the wrong way, or the other option is they tend to apply it in a situation where it's really not needed. And so what I'm showing here is actually a very common situation where really it's not needed. Now, what about if we have the situation where the analog return or the analog system is operating at very low frequencies? Well, with analog systems operating at very low frequencies, as we discussed before, the analog return current may not be so predictable. So if we have our analog subsection here operating on this side of the board, and eventually it has to return here to this region where we joined our two grounds, we may not be able to track where that return current exists, and it may want to flow close to the region where we have digital routing. And so that's where we create the potential for mixed signal crosstalk, where basically the digital section can induce some noise into the analog section, and maybe that interferes with your signals on the analog side. And so the result is that there it actually makes sense to do some kind of variation of star grounding just for the analog side in order to control where the analog return current exists. So this is actually something that's done in audio. In audio, in some audio systems, as has been explained to me by some other audio designers, it is actually common to just route the analog signal and then route the ground for that audio signal right alongside it. So now you're totally controlling where that analog signal exists and where its return current exists. The other option is to just do everything differential on the analog side, right? So differential is quite common in analog. Again, you can find differential ADCs, you can find differential amplifiers, you can find single-ended to differential conversion options for your analog front end, and that also allows you to control where this return current is located. Now, one thing that often comes up in these kinds of systems where we start adding mounting holes is ground loops. So ground loop noise problems with mounting points. I always like to ask, is it worse in digital or in analog systems? Well, I don't think it really matters. Here, when we have a system where we might be, let's say, attaching the system ground over to, let's say, an enclosure, there is the possibility of forming a ground loop. But I think ground loops are really greatly overly exaggerated in PCBs, except in certain instances. And so I think that's something that is worth talking about in a session on EMI, because it's really an EMI problem. It's also a problem that arises when you have a system that has to connect with earth. So for example, when it has an AC input and you're bringing in the earth connection into the PCB. But in many cases, when you have these situations where you have multiple stitching vias connecting between grounds in order to provide consistent potential everywhere in your PCB, the most common objection I see to that, usually from beginners, is that, well, you're creating a ground loop here. The ground loop that you're creating is probably so inconsequential that you'll never be able to measure it. So I would say focus on providing clear ground first, and then worry about the ground loops later. The, of course, exception to that is what happens if you're dealing with earth. Well, earth systems can, of course, experience ground loops, and I think that's something we would have to talk about in an EMI section because, of course, we have a lot of material to get through in this presentation. So here is an example of bad grounding implemented in practice. So this is an example from a project, and here the original designer for this project basically attempted to apply some isolation for the component in this board. Now, here in this board, basically what they're doing is they have an interface here, or they have a component here. They have a header up here on the top. That header admits some signal. The signal travels in here to this component. The component does some computation on that signal and then outputs some digital signals going to the left. And basically what they've done is they tried to create this ground island for these signals. And so what they did is they had this ground island that was basically disconnected from all other regions with ground. And so we had two differently named nets. Here we had the ground net, and then here I think this was supposed to be called like the system ground net. And basically what they did is in routing these traces across this split, what they did is they placed two capacitors on each side of this group of signals, and then they realized, oh yeah, these capacitors provide low impedance return current across this section of the board, but what they don't do is they don't provide low frequency return current because these capacitors have high impedance at low frequency. And so then, of course, they added a ferrite bead here. And the ferrite bead at lower frequencies is basically an inductor. Okay, so they're basically using some inductance and capacitance to connect these planes. Well, what's the problem with this? Well, the problem with this is that you now have an inductance in parallel with capacitance, and then that creates a filter. So that filter being used to connect these two sides of this PCB, that ended up creating a radiated emissions failure because you basically have nowhere for this return current to travel from this side of the board over to this side of the board, and it created strong radiated emissions. And in this instance, once we removed the inductor and the capacitors and then replaced everything with a single plane, guess what? They passed radiated emissions testing. So I bring this up because this is probably the first thing I look for when a client comes to me and says, we're having trouble with radiated emissions failures and we can't pass pre-compliance. Can you help us? This is one of the first things I look for. Did they split grounds? And then the second thing that I look for, which is corresponding to this, is if they did split grounds, did they try and route over these two regions? Now, there are instances where you can split grounds, and I'll discuss that a little bit coming up. But for the most part, this is something that should not be done, and especially if the only reason to do it is to confine noise. So the right way to do this would have been to create this digital zone and this analog zone. And so this image that I'm showing here is a very common image. I think it originally came from a blog from Eagle before it became Fusion 360 many years ago. But I think it's a decent way to think about how to approach a layout and placement for a system where you have some analog stuff and your digital stuff. So your digital stuff can exist in one region, and then your analog stuff can exist in this other region. And then you kind of have this no man's land in between them where you can route the portion of signals that allow your digital stuff to talk to your analog stuff. So this would be your interface, for example, from your microcontroller that would then be used to control whatever analog stuff on your board has a digital interface. And most commonly, that is, for example, your microcontroller then talking to your DAC or talking to your ADC, or maybe, for example, a programmable amplifier, some other component like that. This no man's land would be the region where you want to route that stuff. All your other digital stuff you'd want to place up in this region so that it can talk to each other. And then same thing with your analog stuff. Your analog front end, you would want to try and create this flow coming away from no man's land and then existing only in these regions in order to confine that analog signal in one region of the board. So I mentioned there are instances where you can have non-uniform ground and things will work out very well. So what are some of those instances? Well, the most common instance where you actually do need to have separate grounds is where you have a system that is galvanically isolated. Now, galvanic isolation is something where you are attempting to provide a safety or protection at very high voltage. Okay, and so splitting two regions so that they are disconnected from each other is the safest way to do that. Isolated switching power supplies, of course, is the main instance where you would do this. What's another instance? Well, you can do this with low-level analog and digital. The problem is that most people don't do it correctly. So there are instances where you can do this. The other instance where you can do this and you can get signals across that gap is with optical coupling or inductive coupling, but most commonly this is going to be optical coupling. And so just in this example, could they have done this and done it correctly? Well, it is possible they could do this correctly. They just would have had to do optical coupling here. Now, did they need to do this and have to use optical coupling? Well, clearly no, because when this board was reworked, it passed radiated emissions testing and everything else worked just fine. So they didn't even have a good reason for splitting the ground here in the first place. And so because they didn't have a good reason for splitting ground in the first place, there's no reason to then put an optocoupler here to try and conduct or to try and couple these signals across these two ground regions. Next, systems with chassis ground. This is, again, more of an EMI thing, but it does come up quite often, including in mixed signal systems where you do have a metal chassis and possibly where you have an earth connection. So typically, chassis would be, quote unquote, a separate ground region if the system is earthed. However, you could also have a chassis that then ties to the system ground in certain ways. This does create potential problems with common mode noise. Now, common mode noise in a mixed signal system is one reason that we might like to use a differential interface for our analog signals, because as you should know, differential signals are read by taking the voltage difference between two conductors. And when we take the difference between two conductors, we of course immediately eliminate any common mode noise on that interconnect. So if you do have problems with common mode noise, switching to differential is very useful. So isolated power supplies. I always bring up isolated power supplies. This is a very good skill, I think, for any designer to have, which is to be able to just lay out a really basic isolated power supply and to be able to then track where the different regions are for your board. So here, this is a flyback converter example, which I've shown in a recent video, and we actually built this and then tested it. And the video for the test, it's a very brief video, but it will be coming out pretty soon. And, we built this, we tested it, it works just fine. It puts out the 3.3 volts. And this is just kind of a basic idea showing what the layout looks like. So here, coming from the input, we have a 120 volts input coming in. We have a fusible resistor here to provide protection. And then we have some capacitors here, again, for circuit protection. And then also for rectification, here we have our bridge rectifier. And then here we have our transformer for our flyback converter. And then we have our switcher down here in the central region of the board. So here, it should be very, very clear where the demarcation is between our primary side ground and our secondary side ground. The primary side ground and secondary side ground separate right here underneath the transformer. And then what might not be so obvious is right down here, U9, as you can see where my mouse is, U9 provides that optical coupling for the feedback loop back over here to the switcher. So U9 being an optical coupler, it doesn't require a ground to be bridged across these two sides. It's basically just using light to connect a signal from the right side over to the left side. So the question then becomes, can we or should we ever bridge these two grounds? Well, one of the main reasons that you use a flyback converter is so that you can provide some galvanic isolation between this 120 volts AC input on the left side and then whatever your low voltage is here on the right side. So in this case, it's 3.3 volts. So basically, if I'm ever interacting with the 3.3 volt side of this flyback converter, ideally, I'm never going to be exposed to 120 volts AC input. And so we maintain that by ensuring we have these separate grounds. Now, one thing that you will often see in isolated power supplies is to use what's called a safety capacitor. So these grounds in these isolated power supplies can be bridged if you have a safety capacitor. So what is a safety capacitor? Well, basically a safety capacitor would be connected across GND and then the primary side ground over here on the left-hand side. And that safety capacitor would provide a path for high-frequency noise originating on the right side to then travel to the left and then get back to the neutral here on the left side. So very important in isolated power supplies because it's used to control noise that might otherwise appear as radiated emissions or as conducted emissions from this power output that originates on this right side. So if you ever see this instance where you have here secondary ground, and then you see this capacitor connecting here between this net and primary ground, as I'm showing in this, I believe this is an LLC resonant converter on the left side. Here, this capacitor right here connecting to the primary ground on the secondary side is a safety capacitor. So this would be a Y-type capacitor. And if you're not sure what a Y-type capacitor is or how to find one, just go onto a component search engine, go onto Find Chips or go onto Octopart and search for Y-type capacitor or Class Y capacitor. That would then give you some results that will show some capacitors. You can read all about what their ratings are and what some typical components are. Now, what about the size of the Y-type capacitor that is connected here? Well, here you're basically bridging across this transformer, okay? And the whole point of this capacitor is to ensure that noise can travel between these two regions, and you want that noise to travel through that capacitor as a displacement current. Well, in order to do that, you have to ensure that this capacitance is larger than the winding-to-winding capacitance across this transformer. So what is the winding-to-winding capacitance across this transformer? Well, it can be measured. You can actually measure it, I believe, with an LCR meter. You could also just measure it using a leakage measurement. So basically you apply some signal on one side, you measure the signal on the other side, and then you determine what the capacitance is. Transformers tend to have very good coupling, so they tend to have pretty low winding-to-winding capacitance unless they become very compact transformers. That then increases the winding-to-winding capacitance, and so you would then need to have a larger Y-type capacitor across these two sides of the board. So typical values for Y-type capacitors, they're in the nanofarad range. That's usually sufficient to then control the return current for high-frequency noise that might originate on either side of the board. Now, what's the drawback here? Well, if I place a Y-type capacitor across these two sides of this board, that capacitor has some leakage. So leakage current that then ends up reaching the output side of my board. Of course, if I then touch the output side of my board, I could then experience some leakage current. So some EMI standards have very strict restrictions on leakage current, and the most commonly cited one is in medical. So medical systems have leakage current limits that are pretty strict, and of course you would want to then select the capacitor such that you don't create too much leakage on this output side, and ideally you would want no leakage on this output side in order to comply with conducted emission standards. Next, ground in ADCs. So ADCs are pretty simple to understand components in terms of their core function, right? You have an analog input into the ADC. You convert this to a digital signal on the output, and that digital signal basically is a number that measures the intensity of that analog input, and that digital output can vary over time. Of course, if you're measuring a time-varying analog signal, right? Pretty simple idea. So there is one common guideline which states that ADCs need to have totally separate grounds, or at minimum they should have star grounds. And if you take a look at a typical ADC pinout, especially an ADC like this, which has several different channels, as well as several different digital inputs and outputs, it starts to reinforce this idea that you need to have separate ground nets, such as two different ground planes or a star ground. So in this datasheet image, what you're seeing here is the pinout, and if you start looking at the pinout, you will see here that they have this AGND and then DGND. So basically this says analog ground and digital ground. So this is almost reinforcing or communicating the idea that these have to be separate pieces of copper that are used to connect to these ground pins. However, if you just read the data sheet for this component, on page 6 it says AG&D, connect to DG&D using a single plane. So they're literally telling you, use a single plane for all of these pins. Now, why do we have these separate AG&D and DG&D pins? Well, if you take a look at these AG&D pins, right next to it we have an AVDD pin. So this AVDD pin and this AG&D pin can be connected together with what? A capacitor. Okay, so if we were going to have, so when we have any capacitors that are used to stabilize the analog supply voltage, we would want to put those capacitors right across these two pins. So that's one of the reasons that they're put close to each other, is because we're probably going to have a small surface mount capacitor that needs to connect to these two pins, and so we can place it right here so that it directly bridges those two pins. So that's the first reason. Now, the second reason is because they're actually trying to accommodate best practices for mixed signal layouts. So here on this side, we would want to make sure that our digital stuff is only located in the lower left corner of this component. And the reason we would want to do that is, of course, to make sure that any digital input coming into this component is then going to be confined from any of the analog stuff that might be coming out of this component. Here you can see the analog inputs are all clustered along this top half of this component, and then the digital outputs are in this lower left corner. So this is a very good way that allows us to ensure that the digital stuff can be routed away from the analog stuff and then not create any crosstalk going into the analog interface. So they're really trying to help you route this board so that you don't create unintentional crosstalk. What you wouldn't want to do is take these digital outputs and then route them to the left and then route them up, because you're going to end up routing these digital outputs right alongside your analog inputs. And that would be bad. That would then create the crosstalk that we're actually trying to avoid. So what's another way to look at this? Well, whenever we discuss power integrity, we'll see why this type of connection here that we see on the right-hand side could be very bad. Now, here in this example with this maximum integrated ADC, here we have a few different power inputs, and then we have a few different grounds, right? So we have two grounds, right? We have a digital ground, we have an analog ground, and then we have a digital power supply and an analog power supply. Now, what do we see here? We see a ferrite bead being used to essentially connect the digital supply to the analog supply, or vice versa. So essentially what's happening here is we have power coming in on one of these nets, and then that power is, of course, DC, and then that power is supplying power to the other net at DC. And what's the ferrite bead doing? Well, the intention of the ferrite bead being placed like this is to filter any noise coming from one of these nets into the other net. Then you can see here we also have a reference, or a voltage reference, and we have a couple of different reference connections here. We have a VCC, and then we have a VREF. And then here we have capacitance for each of these power nets going back to their respective grounds. And then here we don't even know if the two grounds are connected. They should be connected, but we don't know necessarily. So why would this necessarily be a bad thing for this type of ADC connection? Well, there are a few things going on here. So first, let's suppose that my digital section needs to output data from my sensed analog input. Okay, so basically, let's say I feed in the analog input here into this differential interface, and then I output my digital data stream. Now, when we do that, the digital supply in here needs to start drawing power, and it draws it in spikes of current. So what happens with those current spikes? Well, those current spikes could actually generate voltage fluctuation at the analog supply. And then that can create some inaccuracy in the analog reading. Now, let's suppose a VDD was also connected to our reference input. Well, now any noise that the digital supply creates on this rail could then get over to our analog reference. And now you've got even more error. So you don't want to have any error on that reference voltage input, because that reference voltage needs to be very flat DC, have very little to no variation, and that will ensure that any result that you read out of this ADC has maximum accuracy. Now, what if we were supplying power through a VDD, and then instead of supplying power through VDD, we had this ferrite bead that then allows our DC to pass from the analog side over to the digital side? Well, that's even worse. Now when your digital signal is attempting to draw current through this ferrite bead, the ferrite bead is going to greatly slow down its ability to draw current from a VDD. And then that's going to create even more noise on this digital output, as well as a lot of noise on this analog input. So this is one of the reasons ferrite beads are so bad in many ADCs. One of the instances where you can probably get away with this, and it's worth inspecting this in simulation or measurement to check that you can actually do this, is the instance where this ADC is only reading a DC analog signal. Right? So, for example, let's say you have a sensor, it outputs a DC voltage level, and that DC voltage level is being read by this differential interface. Well, in that case, your analog supply doesn't need to draw strong spikes of current. It's not continuously adjusting in order to read that input voltage. And so, in that case, it's essentially just reading DC at all times. All you need to do is ensure that all your analog stuff is operating at DC. So that's one instance. Again, it's one of those instances where I would advise checking it either through simulation or much easier through test before you just start placing ferrite beads between all your digital supplies and your analog supplies. So what about VREF? Should we try to, let's say, provide DC voltage between VDD and VREF using a ferrite bead? Well, again, this is one of those things where I would say you probably shouldn't do it. Instead, what you should do is focus on using a precision voltage reference. Precision voltage references are very simple components. They just provide a stable voltage. That stable voltage is also very stable in terms of temperature changes. So they tend to have very low variation with temperature. And those components are not very expensive, so they don't increase your bill of materials cost. And the simplification that you get in terms of routing and in terms of your power topology greatly outweighs the cost savings from using a ferrite or trying to design a filter or use a ferrite to then give power from VDD over to VREF. Now, maybe for your application, for your specific application in a mixed signal design, maybe you do get noise from one of these supplies over to your VREF. But does that matter? Well, maybe it doesn't matter. Maybe the noise is small enough that it doesn't actually have a big influence on your particular measurements. So just keep that in mind when dealing with references, is that sometimes adding these filters in or adding a ferrite to try and act as a filter to then supply power to these other reference ports, that can induce noise. But then you need to check whether that noise is really going to matter for your particular system. So really, I think the best case here is just separate supplies for digital VDD and then analog VDD. They're naturally going to be isolated. You don't need to try and invoke these tricks with a ferrite bead. And then one other step, add in precision voltage references. That will then provide a stable DC voltage for your reference inputs for your ADC. Everything I've discussed for ADCs also applies to DACs. So just remember that. All this stuff with ADCs, totally acceptable for DACs as well. What are some other ways to deal with references? So I brought up a precision voltage reference. However, you can also use what's called ratiometric referencing. So ratiometric referencing is shown here on the left. With a ratiometric voltage, basically what you're doing is you're stepping down the source voltage that's being used on your analog input. That's actually quite useful in some cases, because sometimes the analog input, or at least the full range of analog input voltages that you need to measure might change. Right? Let's say your analog input signal is, let's say it's 100 hertz, and in one instance it's 5 volts, but then sometime later it's 3 volts. Well, you can ensure that you always use all of that dynamic range by also allowing your reference voltage to adjust by a comparable value here using a voltage divider. So basically, whenever your analog input signal level drops due to a change in the source voltage, it also changes the reference voltage going into the ADC, which is then used to read out that analog signal into a digital number. So in doing so, you're basically just setting up a voltage divider here and stepping down your source into a reference voltage. So this is a very simple way to do it. But if you're not familiar with ratiometric referencing, and you know that your analog input signal is always going to have the same voltage range no matter what, then you should just avoid ratiometric referencing and just go with a precision voltage reference. Now, I mentioned briefly, what should we do in order to, or can we, let's say, use some filtering to pull power from VDD over to VREF in order to provide a stable voltage reference? Again, you can do it, but this is one of those things where you really do need to simulate what happens on the digital bus and look at the noise that then conducts over to VREF. So it might be, in your particular case, for your particular digital interface, operating at its edge rate, that whatever noise does get conducted over to VREF is inconsequential, or it could be sufficiently filtered with capacitance on VREF. Now, again, this is something that's a bit more advanced. It's related to the topic generally of power integrity in digital processors that have multiple voltage inputs, sometimes operating at the same voltage level. So a common case on large processors is where you have your standard digital I/O supply, but then at the same voltage you have another supply, such as for PLLs, which are used to generate clocks internally in the processor. In that case, sometimes people will try to use the exact same strategy that I mentioned here in this bullet point, which is to basically apply a filter between the standard digital input and then that auxiliary input that needs to operate at the same voltage. Here with VREF, this VREF is actually not often the same voltage as VDD. Just as an example, in this component I'm showing on the right, VDD could be, for example, 3.3 volts, right? That's really common. But here on the left, VREF could be much smaller. It could be 1.25 volts. So that's another thing to consider here, is that if you did want to step down voltage from VDD over to VREF, well, then at that point, you're basically just doing ratiometric referencing, as we show here on the left-hand side. So all of those different things are very important to consider when setting up your power for your ADCs. Now, what if you did need to read a low-level signal, or you needed to read a signal in a galvanically isolated system, and you needed to make sure that you maintain that galvanic isolation? Well, we have something called an isolated ADC. Isolated ADCs are one of my favorite components. They don't get the attention I think that they deserve, but they are very useful for these instances in mixed signal systems where we also have this requirement for galvanic isolation. So essentially what we would have here is we would have a digital ground and an analog ground, again, galvanically isolated. Here we have a specific reason that we want to split into two separate ground regions. And that reason is safety. That's the main reason that we have galvanic isolation. And we would then bridge these two, of course, with a Y-type capacitor. If we have an issue with radiated EMI at high frequencies, we can help control that with this Y-type capacitor. And then here you see that we have our isolated ADC bridging the gap between these two sides. So these components have an isolation barrier built into the component. They're inherently isolated internally, and there's the digital interface on one side. All of this digital stuff is isolated from all of this analog stuff on the other side. Here what we have is we could have a VDD that then also has an internal micropower DC-DC converter built into it, which then provides power over to the other side. But sometimes what you see is you'll actually see an analog power pin on this other side. So what you would have is you would have basically a digital power supply on one side and then an analog power supply on the other side. But that's not always the case, as you can see here in this component on the lower half. So here's another example of usage of an isolated ADC, which we showed in a video. This example shows just a dual ADC module. Here we have our isolated ADC in this upper left corner, and then down below we have our standard ADC. And then basically what we're doing is we have 3.3 volts on the right-hand side, which then supplies all of the power pins for the standard ADC, as well as the isolated ADC on the digital side. And then here on the left side, we would have a power input on one connector. So we have a 5-volt input. And then we have our signal for our analog signal that we then want to measure with the isolated ADC. Now, here, this is very important because what I'm doing is showing all layers in this Altium Designer project. So I've dimmed the polygons just a little bit so it's very clear, and you can see that we are looking at multiple layers. You can actually see the traces on the back layer going up to this pin header. But what you can see here when we have all the layers turned on is that we have a gap between these grounds that spans all the way through this section of the PCB. And then you can see here that there's nothing being routed between the two sides of this system, okay? So if you did have separate grounds, as we have here, with the purpose of maintaining galvanic isolation, once again, you do not want to route between these two sections. Instead, you want to focus on setting up your layout such that you don't need to do any routing between these two sections, right? So I wouldn't want to start putting a bunch of digital components over here in the upper left-hand corner and then trying to route digital traces across this gap. That totally defeats the purpose of separating these grounds with the purpose of maintaining galvanic isolation. Instead, what I would want to do is keep all of the digital stuff on this right-hand side. Now, in this module, as you can see here, this analog input comes in. Well, this should be obvious. This is an SMA connector, and then just goes straight into this isolated ADC. And the way that this has been done is I've provided ground pour everywhere, and then I stitched everything together with stitching vias. You can see that down here as well for this analog input. Now, this analog input could be a pretty low-level signal. And in fact, if you start looking at the voltage ranges that can be sensed with an isolated ADC, they're not huge voltage ranges. As I recall, the part number that was used in this project, it had a full range voltage of about 1.25 volts, if I recall correctly. So these are really being used to measure a low-level analog signal in a noisy or unsafe environment where you would need galvanic isolation. Next, something that is, I believe has been actually discussed by Eric Bogatin in mixed signal design, is what happens when you have different voltages and different power rails, and what happens when you start to overlap them. So basically the question here is how, if I need to have uniform ground for my mixed signal system, how should I set up my analog planes and my digital planes in order to ensure that I don't get an EMI problem? Well, I think most people would say, wait a minute, you're saying my analog power region and my digital power region can create an EMI problem? And the answer is yes, they actually can create an EMI problem, and that would be observed as radiated emissions through the edge of the board. So when you have, for example, power rails at different voltages and that supply different types of signals, and you allow them to overlap, as I show here in this drawing. Here what we have is a voltage at V1 and then a voltage at V2, okay? And V1, for example, could be a digital supply. That digital supply could be taking in strong spikes of current. And so it could be, it will have a time varying voltage associated with it. V2 could also be a digital supply, or it could be, let's say, an analog supply. And so it could be operating, it could be time varying as well. The capacitance between them determines the current or the displacement current that starts moving through this capacitor over time. And so that's given by the equation on the right. Basically, it's based on the time differential of the difference between these two voltages, right? It's pretty basic equation from electronics. So here, if V1 and V2 were perfectly DC, these are perfect DC rails, we have absolutely no change in the voltages over time, then of course we don't have any potential EMI problem due to these overlapping analog and digital planes or overlapping digital planes, okay? We would basically have a zero displacement current here, and we wouldn't need to worry about this. The reality is that whether you're dealing with a digital power rail or an analog power rail, they do vary in time. And so what you see here tends to happen when you start to get to higher layer counts, or you need to have one layer that carries so much current that it has to, the only way to get enough copper is to put it on its own layer. And so the result here is that when you have this, what you have is you basically have a time varying electric field that exists across this plane. And so what happens when you have a time varying electric field and a time varying current that exists in this region? Well, you then generate an electromagnetic wave. Okay, so that's exactly what creates an electromagnetic wave. And then that would then be observed through the edge of the PCB as radiated emissions. So the best option here, if you have this situation, is to separate these rails on the same layer. So this gets back to the power layer that I mentioned much earlier when we were looking at the different types of stackups. If you have a dedicated power layer, you can use that power layer for multiple rails, as I show here. So you can have your analog power, you can have your digital power at one voltage, you could have a digital power at another voltage, as many as you need. And what you would then do is place them over ground on the very next layer. So this is one way to use that signal power ground signal stack up effectively in order to eliminate this potential radiation problem when you have overlapping power rails. So basically what I'm saying here is we would not want to then take, let's say, for example, DC1 and then put it up here above this analog supply and then route it, because then we potentially have a mixed signal EMI problem. So as I mentioned above, we have situations where generally it is best to have a single ground region unless you can prove you need separate grounds. Sometimes cutouts are used to ensure devices operate correctly. Sometimes you're recommended to use a cutout, but you actually shouldn't use a cutout in order to ensure devices operate correctly and that they'll pass EMC. Some instances here in mixed signal designs are, of course, when you have switching nodes or switching regulators. Another one that is near and dear to my heart is when you have an impedance matching circuit, and this is actually quite common when you start looking at some microcontrollers that have an RF interface. Another one which is related to the impedance matching circuit issue is when you have an SMA pin. So some SMA connectors, the pad on that pin is actually very large, and you may need to implement cutouts in order to ensure that this interface operates correctly. So let's go through some examples. So here what I'm showing in this image is something which I have discussed in the video, which is switching regulator, and specifically the inductor in the switching regulator. Now, in this switching regulator, you can see here, I have an inductor with the switching node output very clearly denoted, and the output node here is a 5-volt output. Now, here, a cutout has been applied below the inductor. And this is one of those instances where it's a guideline that keeps coming up, and I see some people implement it just kind of without question. And so the question here is, should you use this ground cutout below the switching node or below this inductor? if you start to look at the parasitic capacitance in various portions of your circuit, you start to come to the conclusion that you actually don't need this ground cutout. So one of the objections to using this ground cutout is that you will lose some efficiency. And the reason that you would lose some efficiency is that if you did have ground here, you would have some capacitive coupling between the switching node into the ground. And basically what that means is that some of that power would be lost directly into the ground instead of being conducted over to the 5-volt output here on the right side of this inductor. Now, if you start to look at the capacitance across power MOSFETs, that capacitance across power MOSFETs tends to be much larger than the parasitic capacitance associated with this switching node. And so the result is that if we did include ground below this inductor, you would only get a very slight reduction in the efficiency. Now, there are some exceptions to this, right? Let's suppose that we're using much faster FETs, right? Well, if we have a faster FET, then the capacitances in this FET are going to be smaller, and they could become closer to the parasitic capacitance from your switching node. Sometimes your switching node is made very, very large. So we actually want the switching node to be large because it tends to carry high current. And then we also want to reduce spreading inductance associated with that switching node. But of course, the trade-off is that you get larger parasitic capacitance. So you could then get a larger reduction in efficiency. Now, I think all of those issues are offset by the fact that when you do have a faster FET and you do have faster edge rate, you are going to have greater shielding for radiated emissions in this design and greater shielding for crosstalk into nearby analog or digital interfaces when you include this ground plane. And this is because the magnetic field will not be able to radiate or pass, I should say, through this cutout through the entire board and then be observed around the PCB. Now, we can see very clearly in some radiated emissions measurements that the ground does provide a significant EMI benefit. And this example shows CISPR 25 connected emissions tests. And you can see quite clearly here what happens when we include ground below that inductor. We get what was a failure now turns into a pass. So just backing up for a moment before getting into impedance matching networks. Now, one thing I'd like to note is that, this is just showing a specific type of inductor. This inductor could be a shielded inductor, so that will also help prevent the leakage of any magnetic field around the inductor. But of course, there are also for example, toroidal inductors. There are also horizontal inductors, basically wire-wound inductors. This particular inductor is a vertical inductor, but it could be shielded. So there are different types of inductors that will also help reduce the escape of that magnetic field around the inductor. Now, that's very important because in mixed signal boards, you might be routing something nearby this power circuit, and that's especially the case if you're dealing with a mixed signal board that's getting rather dense. And so if you are routing something nearby this power circuit, then you would definitely want to include the ground below this inductor, and you would also it would also be a good idea to consider a shielded inductor. So shielded inductors, especially in this package format, very common. You can get them from Worth, you get them from Pulse, you get them from Murata. All sorts of different vendors provide shielded inductors, very marginal on additional costs. So I recommend going that direction. Next, ground below impedance matching networks. So as I mentioned, this is typically the case you will see when you're dealing with RF designs or when you're dealing with a digital design that has an RF interface. So I would also consider this to be a mixed signal design. And actually these microcontrollers that have these RF interfaces also tend to have an analog input for an ADC. So they definitely are mixed signal components. Now, if you're dealing with an RF design, that RF trace needs to be treated in a very similar way as the digital trace. It should be, the ground should be provided close to that trace, and that will help confine the return current from that RF interface. Now, here what we're showing, of course, is the signal coming out of a microcontroller, and you can just see the edge of the microcontroller here in the upper half of this image. And then that trace is passing over ground, and it's basically a coplanar waveguide. However, in this particular component, this component on its RF pin has an output impedance of something like 30 plus, 30J for its impedance. So it basically has 30 ohms worth of reactance. Not all RF components operating in the Wi-Fi range are like that. But one thing I've noticed with with a lot of these microcontrollers that are operating at the 2.4 gigahertz range, or they're operating at 5 gigahertz or 6 gigahertz in order to target things like Bluetooth and Wi-Fi, is the chips are actually designed such that they do have this output impedance of something like, like I said, 30 plus 30 ohms resistance and then 30 ohms reactance. And so it's your job as the designer to then apply an impedance matching network to transform that impedance into a output impedance that matches your antenna. And that's the whole point of these impedance matching networks. So that's what's being done here is we're applying a CLC, a pi filter impedance matching network. And you can see here that this has been applied above a ground cutout. So here the purple region is ground on layer 2, and this is a 6-layer board. And what we've done here in this region is we have cleared the ground from layer 2 to layer 5. Now, why have we done that? Well, the reason is that this ground is actually creating additional parasitic capacitance around the pads and a trace in this interface. And what that's doing is it's creating some deviation in the performance of this impedance matching circuit. So basically, on paper, this impedance matching circuit is designed to provide a perfect match between this RF interface and this antenna. But once you actually put it into the PCB layout, the ground creates additional parasitic capacitance and additional parasitic inductance. And so the components that are placed in this impedance matching network perform as if they had different values than what you put into your schematic. And so you can actually calculate what that deviation is. Just by clearing out some of the ground around these components, you can reduce the amount of additional parasitic capacitance, and you can do the same calculation for parasitic inductance. And what that does is it brings the operation of these components closer to the ideal value. Now, you'll still need to tune some of these components so that you get just the right amount of impedance matching, and that can be done manually by soldering and desoldering. Also, Robert Faranek actually has a really good video where he runs over how to do this on a spectrum analyzer with a prototype, and then you can actually observe very clearly when you get optimal impedance matching across this interface. So, Eric, maybe I'll share that video with you once we finish up, and you can share it with folks on LinkedIn. So another fun type of routing that can be used in RF interfaces where you have a connector is something called skip layer routing. Now, skip layer routing here in this configuration is actually quite different from the skip layer routing that's used in packaging or in integrated circuit substrates. Skip layer routing in integrated circuit substrates is intended to reduce crosstalk, whereas the definition in PCBs is to actually allow you to widen out the trace near a connector in order to recover some losses along this trace. So take a look at this side view for this signal ground signal stackup. Typically in this stackup, you'll have the thick core and then the outer layers will be thin. And so that forces you to put ground close to the signal on the top layer. Well, what that does is in order to hit your 50 ohm impedance requirement, which you might find for an RF interface, this requires this trace to be rather thin. Once you get to the region with the connector, you can actually eliminate some of the losses on this last mile of the route by cutting out the ground just in the region of this connector. And you're cutting out the ground only on layer 2. What that does is it allows you to widen out this last portion of this trace. And then by doing that, you can recover some of the losses that would have otherwise been experienced by just routing this line straight in. So this was originally introduced to me by someone who used to work at Qualcomm. They're now at Amazon, and he stated that they actually do this in their packages that they design at Qualcomm. So there are 5G phones out there that actually have this kind of routing in them. So if we're designing, let's say we have our mixed signal PCB, it has an RF interface on it, and we want to do something very similar going into a connector pin, what would this look like in the PCB layout? Well, this actually shows an example of what that looks like. Excuse me. So here we have an 18 mil wide transmission line on our top layer. It's being routed away from anything else that might be nearby, and it's being routed directly into a connector pin. And here somewhere on the left, we basically have our microcontroller with our RF interface and any required impedance matching in order to match to the impedance of this trace. Now, here we have a transition region where we've applied a taper. So this taper is intended to very gently smooth out the impedance transition between the thin trace and the wide trace. And what that does is it reduces reflection for the signal coming in on this RF line and then going into our connector pin. Now, this is where we get into another practice with applying cutouts, which is on SMA connector footprints. Now, SMA connectors basically have a central pin, and then there are some side mounts here that grab onto the PCB, and those are part of your ground connection for your SMA. So I'm not showing the paste mask or the solder mask layer here, but here you would basically have solder mask opening on the left and the right side in order to allow for soldering of this connector onto the board. Now, when you're operating at very low frequencies, this is an issue with RF design just generally. When you're operating at very low frequencies, we're really not worried about the impedance of this pad. And that's because of input impedance considerations. And again, maybe that's something we discuss in an RF design session. But here we have our 50 ohm line, and then it's coming into a 14 ohm pad. And the interface between this line and this pad creates some reflection. Okay. Now, one thing that we're doing along this RF line is basically what was done in the other mixed signal board that I showed earlier with the impedance matching network, which is basically just placing some vias along this line in order to confine the field around this trace and help prevent any sort of potential crosstalk from anything else that's nearby, and then prevent strong radiation from this trace. Now, that sets the impedance of this line to 50 ohms, but then when we get that 50 ohm line over here to our connector, we then have this interface here where we then have the potential for some reflection. And so we want to overcome that. What's the easiest way to overcome that? Well, we could do a few different things. We could apply a taper. We could apply a taper and a ground cutout, or we could try to do some kind of impedance matching network. I strongly recommend against trying the impedance matching network because there are much simpler solutions, such as just adding in this taper or providing some ground cutout here. And so here on the right, what I'm showing is a comparison of the S parameters for this interface operating up to it's almost 7 gigahertz, so just above 6 gigahertz. So here in the original design, which is just this interface here, that's the no clearance, no taper line here. And you can see very clearly we have way too much reflection. The S11 curve passes pretty high above our 10 dB typical limit, and in that instance, this would be considered a failure for this interface. So we've done everything right in this RF design except the transition right here. So in order to fix that, if we just apply a taper and we then apply the ground clearance, we can see here that up here around 10 dB, we get a pretty significant reduction from the original case where no clearance and no taper was provided. If we just provide ground clearance, where we cut out some of the ground below this pad, and then that sets the pad's impedance to 50 ohms, we also get a pretty big improvement. So you can see here in different frequency ranges, you get different levels of improvement in the interface looking into this connector. So either case is going to be an acceptable measure here, especially when you start to look at, for example, 2.4 gigahertz, which would be a typical value that's used in many microcontrollers with an RF interface, or once you start to look up here in the higher Wi-Fi frequencies, both of these would be acceptable. And then this SMA connector could then, for example, it could be used to connect to a coax line, could connect to, for example, an antenna that has a coax input. So all sorts of things you could use this connection for. Next, I brought up stitching vias in several instances. Now, in mixed signal boards, one of the typical use cases that's cited for stitching vias is to basically act as a shielding mechanism. And this is sometimes called a via fence. This is sometimes used to segment different areas in a PCB layout, such that you have a very clear demarcation between two regions of the board. For example, your digital board, or your digital part of your board, and your analog part of your board. So in this via fence operating in this board, what you can see here is you have some exposed copper, and this exposed copper would be used to contact to a shielded enclosure. But then you have a bunch of vias along these different portions of the exposed copper. So what these vias are doing is the density of these vias is determining their potential shielding effectiveness. And it is that shielding effectiveness that is sometimes exploited to then define, for example, clear demarcations between an analog region and a digital region. And that's basically what's being done here. Now, I think what you have to remember is that this is also being used to connect this exposed shielding to internal ground. So that way you're basically creating a bunch of Faraday cages around these different portions of these circuits. And again, that's meant to provide some shielding between, for example, an RF section, a digital section, low frequency analog section, and possibly even a power section. So how do you select the density of your stitching vias? Well, what we care about is basically the wall-to-wall spacing between two of these vias. And so if we're going to use stitching vias to try and provide any kind of shielding between two portions of our system, what we would do is we would select the stitching vias such that the distance between these via walls is set such that we are blocking the wavelength associated with the highest frequency that we want to block. So at some point, the frequency of an electromagnetic wave that originates in this region of the board is going to be so high that it can pass through these vias. And that limit to the highest frequency that we can block with this array of stitching vias is given by the wavelength in comparison to the distance between those vias. So a typical cutoff is taken as, for example, let's say lambda over 8, okay, or lambda over 4. The reason there's no specific value is because sometimes these stitching vias appear in this kind of X array, or this diamond-shaped array. And so, which distance do you use? Do you use this distance? Do you use this diagonal distance? There really isn't a clear cutoff. But typically the highest frequency that we can block is the frequency associated with a wavelength that is 8 times or 4 times the distance between these via walls. So basically take this distance here, multiply it by 8, for example, convert that to a frequency, and then using the speed of light inside the dielectric, and then that tells you the highest frequency that you can reliably shield against using this array of stitching vias. So another typical usage, which is actually really the preferred usage for stitching vias, is also to bridge these ground regions on different layers. Here, this is just an example from Multi-Image Designer, but these stitching vias can be applied automatically in this offset arrangement that you see here. And so what this is doing is this is connecting our pore on the top layer with the internal ground inside the PCB. Now, one reason we like to do this is, of course, when you start looking at what happens with signals that have to transition between two layers. So here we have the MOSI and MESO signals on an SPI interface. Here we have some stitching vias. These stitching vias appear automatically in the board. And sometimes what we want to do is adjust the location of these stitching vias such that they are closer to these signal transitions. And the intention with doing that is to ensure that during this vertical transition, we confine the electromagnetic field around this via near ground, and we keep it near this, we keep it around the via. And in doing so, we can prevent leakage of the field to any other circuits that might be nearby, or in the worst case, prevent creating so much radiated emission that we see it in a radiated emissions test. And so this is done by adjusting the distance between these signals and the stitching via. Now, I will just say, if you're operating below a few gigahertz signal bandwidths, channel bandwidths, I should say, you don't need to intentionally design these via transitions such that you have a very specific impedance. Just put a stitching via nearby, and that's going to be good enough. It's not something you really need to worry about at very much. But once you start dealing with very fast digital interfaces where the channel bandwidth requirement is well above 3 or 5 gigahertz, then you do need to very intentionally design these via transitions such that they have a specific impedance. And one way that you do that is to place these arrays of stitching vias and to engineer the clearance around this via to a specific value. And by doing that, you can then get your via transition to be the required impedance. Now, another good use of stitching vias, I've brought this up again here on the right, you can see is the usage in designing coplanar waveguides for RF sections in a mixed signal board. Now here in this example, what we have nearby in the left is we have an RF interface connecting to what is basically a module, and then this module comes in with this pad and this through hole. And then we have a bunch of stitching vias around this module, or around this trace leading into this module. Now, these stitching vias are able to shield against all of the power components that are actually nearby this interface. And so I bring this up because this particular system is an RF power supply that also has a digital interface on it. So there's a microcontroller and some power components around this board, and all of those could potentially couple noise into this interface. Now, in this example, you don't see a lot of those components nearby, and that's because in this particular design, the placement was done such that we prioritized providing space around this line. So this is another very important point here, is that stitching vias help, but they are not the magic bullet against noise being coupled into this interconnect. Really, the best tool that you have at your disposal is using ground planes and then placing the components and circuits such that you don't have strong coupling between these different elements into this interconnect. What's another good usage of stitching vias? Well, I've talked about them on ground so far, but they can also be used on power nets. So a good use here for these stitching vias is actually to increase the current carrying capacity between this rail and whatever its connecting rail is on a different layer. And so you can see here I've used an array of 8 stitching vias. It was originally designed as 9, So there would have been one right here on the VDD pad, but of course, wanting to eliminate via in pad, I just deleted that 9th stitching via. But yeah, this is a pretty standard practice here in power systems in order to increase the amount of current carrying capacity that's allowed on this net. Now, the other thing that it does is it reduces the inductance along this net. So if this rail, for whatever reason, is connected to, let's say, a switching element or a large inductor, this reduces the amount of additional inductance due to the presence of these vias on this layer transition, because you basically have 8 vias in parallel here. And so you would expect sub-nanohenry levels of parasitic inductance along this vertical transition. So I get to that number because typically a single via about 1 nanohenry of parasitic inductance. You take 8 of them in parallel. That's 1 divided by 8. That's about 0.125 nanohenries. Next, guard traces. So I alluded to this earlier. What happens when you have a guard trace, and how does it affect crosstalk in different situations? Well, typically, when we use guard traces, we're just running a guard trace along a signal trace, and then we terminate it at one or the other end. And, you know, the 50 ohms terminated and open terminated situations are really not relevant. Normally, guard traces are just terminated to shorts at both ends. And so we can then use that to examine what happens with crosstalk due to the presence of the guard trace. And what we actually see here is that when we look at microstrips and strip lines, we get different effects on crosstalk. We also see that short termination doesn't necessarily always produce a reduction in crosstalk. So here, when we look at the microstrip case on the left, we see that when the guard trace is applied and it's shorted at both ends, we see here that the results are pretty not useful, I would say. Here with the short terminated case, on near end crosstalk and far end crosstalk, we see that when the guard trace is applied, we only get a marginal reduction in crosstalk for the microstrip case. Here we can actually see that the crosstalk is actually resonating in some way, as you can see from these multiple peaks arising in this time domain readout. Now, what about the case with strip lines? Well, with strip lines, here with the short terminated trace, we can see that in the case of far end crosstalk, we get a reduction with the guard trace, but the crosstalk was already so low anyways as to really be inconsequential, and we wouldn't need to worry about it. Now, what about the case with near-end crosstalk? Well, with near-end crosstalk, this is where we would get significant reduction in crosstalk with the guard trace. Now, you can see here that when there's no guard trace, we get about just over 3 millivolts of crosstalk, and then when we add the guard trace, we get less than 1 millivolts of crosstalk. So that's pretty good. I think no one's going to complain about that big of a reduction in crosstalk, but the point goes that this really only works for near-end crosstalk problems in strip lines, and it's not something that you should apply universally, and especially not in microstrips. So this is the last slide, and it brings up one of the perils of using guard traces with a bunch of stitching vias, and it illustrates what happens in the microstrip case. So this was brought up by Eric Bogatin in one of his Altium Live presentations, and I always like showing this because it really illustrates nicely what happens with the stitching via spacing here along this microstrip in order to provide the short circuit termination. And what you can see here is that these via spacings actually create a resonant cavity. And we know they create a resonant cavity because we get this peaking behavior, which then persists and repeats over time. Now, when we create, excuse me, when we make that via spacing small, eventually what happens is we push off those resonant frequencies to much higher values, such that we have less of the aggressor signal power spectrum overlapping with these signals. And so that's why when we have smaller via spacing, it is possible to get a reduction in crosstalk. we see it's not a huge reduction, but it is a reduction in crosstalk. Now, in this case, where we have small via spacing and we have a low loss material, we can actually excite some resonances here that then bounce back and forth between these vias, and then that generates what we see here, which are these two instances with the black curve and the purple curve, and then those two instances generate this strong peaking behavior and oscillation that we see along this interconnect. So point going here, be careful with just applying guard traces and stitching vias. A much more effective strategy in really any PCB, and not just mixed signal PCBs, is instead bring the ground plane on the next layer closer to your signals if you're having a problem with crosstalk. So this is something that I discuss in a talk on packaging and HDI design, and again, maybe this is another session that we can do here in the future.